Okay, folks, so now we're ready to talk about the second principle of superposition, and this is a principle for non-homogeneous equations. So again, consider the nth order linear ODE, and notice that this is non-homogeneous if f of t is not identically 0. Then we can go ahead and we can give the nth order linear differential transformation or linear differential operator that is the left-hand side of that ODE. Okay. Finally, if y of h satisfies the fact that L of y of h equals 0, then that means that y of h is a solution to the homogeneous equation. This is not a homogeneous equation if f of t isn't 0, but I could find a corresponding homogeneous equation for which I do set the right-hand side equal to 0. If y of h satisfies that, and y of p satisfies the ODE, then we can give the general solution as the family of homogeneous solutions plus the one particular solution. And that will solve, not only will that solve the original ODE, meaning that when we plug in that y, it outputs the right-hand side, but in fact it turns out that all solutions can be written that way, in which case we found a general solution. Okay. That's very abstract. Let's go ahead and first give some steps and then actually look at an example of this. Okay, fighting with the machine. So here's an outline for how to solve nth order non-homogeneous ODEs based on what we saw above. First, you're going to find this family of solutions to the corresponding homogeneous equation. Then you need to find one particular solution to the original ODE, and then you give your general solution as y is equal to the sum of the family of homogeneous solutions plus the one particular solution, and that gives us a general solution to the original ODE. All right, so here's an example that hopefully will clarify this. So let's go ahead and first confirm that y of t equals the tangent of t is a particular solution to this ODE. So show y of p equal to the tangent of t solves the ODE. So this is just a first order ODE, and in fact you could solve this many other ways, but we're trying to learn how to use this notion of particular solutions versus homogeneous solutions, and how the sum of a particular and a family of homogeneous gives us a general solution. So I know we could solve this through the integrating factor or by some other means, but I want to focus on using what we learned with superposition. So if we take the derivative of this, the derivative of the tangent is the secant squared of t. Let's go ahead and plug everything in. So we get yp prime minus the tangent of t times yp, and we're confirming that this equals 1. Well, that gives us the secant squared of t, that's what we found yp prime to be, minus the tangent of t times our particular solution, which is again tangent of t, and we're checking to see if this is 1. Well, this is just secant squared of t minus tangent squared of t, which, yep, that does in fact equal 1 by the one of your Pythagorean identities from trigonometry. So we have a particular solution. Okay? So I'm running through these steps. We've got a particular solution. Now I need to find the family of homogeneous solutions. So now solve the corresponding homogeneous equation. So now we're going to solve the corresponding homogeneous equation by setting y prime minus the tangent of y, the tangent of t times y, set equal to 0 because we're solving the corresponding homogeneous. That's why we've set it equal to 0 here. Okay. So the beauty of trying to solve a homogeneous especially a first order, is that it's always separable. So we get y prime is equal to the tangent of y times y. Oops, doggone it, that should be the tangent of t times y. And it's separable, so that gives us y prime over y is equal to the tangent of t, or multiplying both sides by dt, we get that dy over y is equal to the tangent of t dt. Integrating both sides gives us the natural log of the absolute value of y is equal to, what's the integral of the tangent? As I recall, that's the natural log of the absolute value of the secant of t plus c. Raising both sides over e gives us the absolute value of y is equal to ce to the absolute value of secant. Oops, gives us, well, let's go ahead and write it this way just so we don't do too many steps at once. In fact, let me do this over here as well. So we get e to the natural log of the absolute value of y is equal to ce to the natural log of the absolute value of secant t, where we absorb this constant as you've seen me do in a few other examples. Well, we can go ahead now and just equate these two, we can go ahead now and simplify these two sides using my properties of logarithms and exponentials. So we get c times the absolute value of the secant of t. But notice, because we've got this arbitrary constant here, it's enough just to say that y of t is equal to the c times the secant of t, where, because we would argue this, it could be plus or minus, but it could absorb some of the constant, and likewise over on the right hand side. Okay, so what did we just find? We just found the family of homogeneous solutions to the homogeneous ODE. So what do we have to do next? Well, superposition tells us now that we're done, because we can now give the general solution of y of t is equal to, how did I write this? The family of homogeneous solutions, that's this, c times the secant of t plus one particular solution, and we've already confirmed that tangent of t is a particular solution to the original ODE. So there's our solution. I'm going to go ahead and stop here, and I'll make one more video on this topic.